Okay, let's finish off this chapter talking about atomic spectroscopy for the hydrogen atom, ending up with the Rydberg equation. Recall the Bohr model of the atom, where you had the nucleus and the electrons were going around the nucleus in orbits, n equals 1 orbit, n equals 2 orbit. Well, it turns out these orbits from the Bohr model of the atom also are the orbitals in the quantum mechanics model of the atom. These are the n equals 1 shell and n equals 2 shell. However, when Bohr originally thought that the electrons are moving around in orbits around the nucleus, we now know that they are just somewhere in this volume of space around the nucleus, and so n equals 1 is an orbital. The electron is somewhere around the nucleus. It is not, in fact, orbiting the nucleus in a circle. However, the quantum mechanic shells n equals 1 equals 2 do correspond to the Bohr models n equals 1 and n equals 2 orbits. And back in Bohr's day, he had an equation, or there's an equation that would allow us to calculate the energies of these orbitals. And here it is, the energy of any orbital, any quantum shell, equals negative 2.18 times 10 to the minus 18th joules, that's the Rydberg constant, times 1 over the number, the shell principal quantum number squared. So easy, if n equals 1, we can just do this math really easy because 1 squared is 1. 1 divided by 1 is 1, so the energy for n equals 1 is just negative 2.18 times 10 to the minus 18th joules. That's the energy of the n equals 1. For n equals 2, well, n squared, 2 squared is 4, 1/4 times this number gives negative 5.45 times 10 to the minus 19th joules. I'm sure you can put in 3, 4, 5 and do your calculation for these energy levels. Now, what happens when you have an electron in these energy levels? What happens if you have an electron in the n equals 1, the ground state, the lowest energy state? If you shine light on that electron, the exact right wavelength of light, you can get the electron to, say, jump up to the n equals 2 excited state. The electron absorbed energy from light and jump to the n equals 3 excited state up here. And while in n equals 3, perhaps it jumped down to the n equals 2 excited state. Well, if it lost energy by jumping down to a more stable orbital, then it had to give off a wavelength of light. And you can calculate the wavelength of light. You can calculate the energy of that light using this equation right here. Delta E, the change in energy from the n equals 3 excited state to the n equals 2 excited state, is negative 2.18 times 10 to the minus 18th joules times 1 over the final quantum shell squared, where it ended up. Here it ends up in n equals 2, minus 1 over ni, the initial n equals 3 shell squared. So we can do a sample calculation here. Calculate the energy change when an electron jumps from n equals 3 to n equals 2. Well, delta E equals negative 2.18 times 10 to the minus 18th joules times where it ended up, 1 over 2 squared, which is 1 over 4, minus 1 over 3 squared, 1 over 9. Do the math, you get negative 3.03 times 10 to the minus 19th joules. Now that's the change in energy. The negative indicates that energy was given off. The negative indicates the light was given off. A photon of light was given off from this process. All right, now that gives us the energy, but recall from before that energy equals Planck's constant times the speed of light divided by the wavelength. Rearranging this, the wavelength equals Planck's constant times the speed of light divided by the change in energy. A little math, Planck's constant, speed of light, and our delta E. Note I'm not using the negative here. The negative just meant the energy was given off. This is 3.03 times 10 19th joules of energy. But plugging that in, we get the wavelength of 6.56 times 10 to the minus 7th meters, which is the same as 656 nanometers. And what Rydberg eventually did was he said, okay, I'm going to combine this equation with this equation up here. And when you do that, and you can derive it on your own, you find you get 1 over lambda, 1 over the wavelength, equals a new Rydberg constant, 1.0974 times 10 to the 7th meters to the negative 1, times 1 over n final squared minus n initial squared. And with this equation, you can go directly from the quantum shells, n principal quantum number shells, to the wavelength. But realize, make sure you remember, this is 1 over the wavelength. You have to do the math to actually get the wavelength.